All right, let's open up to page 407. Yesterday we were talking about periodic functions and how we can determine if a graph is kind of repeating itself, where we have a particular section that is repeated over and over and over again. And if a periodic function is what we're dealing with, we could probably identify the period of that little chunk that's being repeated and the amplitude of that chunk. I know yesterday we used the word chunk, but more specifically it's referred to as a cycle. So a cycle is repeating itself, and we'll use that word more often today. I believe we have the last two parts on page 407 to go over. Is that right? Parts D and E? All right. So taking a look at the bottom there, we graphed it yesterday, so we should have that available to us. What are the values of f of 15 and f of negative 77? So if you take a look at the graph, notice how we only have values from negative 11 to 10 available for us. And what they're asking us for is, well, if we were to go to the 15 spot on the graph, what would we get out? If we were to go to the negative 77 spot on the graph, what would we get out? So these are clearly off of our graph, but since we know that this function is periodic, it repeats itself, maybe we can figure out what these values would be. How might you want to do that? Yeah?
I looked for what x value we get with 15 if we were using multiples of 7.
Sure. And what was the 7?
It was 8, like the 8x value.
Okay, so how did you know you had to use 7? What did the 7 represent again?
The cycle.
The cycle, or the period, like how long the cycle was. Perfect. So up in part B, we said that the period was 7. Every 7 units, it repeats itself. So this 15, if it's off of our graph to the right, we need to go backwards a period, or maybe more than one period, so that we land somewhere on the pictured graph that we have. So if we take 15 minus a period, we'll get a value of 8. Very similar to how we found coterminal angles when we were dealing with trig functions. Remember, coterminal are angles that land in the same spot. You could probably think about these as coterminal points. Okay, they are different x values, but the y values are the same. Okay, the y values land at the same height. So we could say that f of 15 is exactly the same as f of 8. Do we know what f of 8 is? Is that on the pictured graph that we have? What'd you find, Tori, when you did it? Negative 2. Yep, we're looking somewhere right there. All right, so f of 15 is negative 2. Even though 15 was not pictured for us, we could use the cycle or the period to help us figure that out. Very similarly, let's try f of negative 77. So negative 77 is way off our graph to the left. That means we're going to have to add some periods so that we travel to the right and we eventually land somewhere on here. Now the question is, how many periods do you want to add? Because if we just add 7, we'll be at negative 70, and that's still really far off our graph. Yeah?
Okay, since this just happens to be like a multiple of 7, I guess, just divide that by 7 and get negative 11.
Let's see. Okay, so maybe we'll say f of negative 77 is the same as f of negative 11. Okay, we'll try to check that out. Since it's divisible by 7, that might be a way to go. How many times do you want to add 7? I mean, we can keep doing it. If we add 7 once, that's negative 70. If we add 70 again, negative 63. If we add 7 again. Yeah? You could add it 11. You could add it 10. You could add it 12. Okay, we eventually just want to land somewhere between negative 11 and 10. Let's say we added 7 11 times. So in other words, 7 times 11. Negative 77 plus 77 would give us 0. So we know f of negative 77 is exactly the same as f of 0. Let's see if that works out with what Tori thought. So if we were to divide negative 77 by 7, we'd get negative 11, and we would land there. But if we add a period multiple times, we should be landing here. So I'd say it might not work out that way. Okay, but that was a good guess, or a good thought. All right, so f of 0 is 2. All right, do you guys think you can try part E? Try to figure out where f of 64 would land, or f of negative 25? Let's see, were we able to find a coterminal x value for 64? If you kept subtracting 7, where would you eventually land? You might have different values depending on how many times you subtracted 7. Did anybody find one? Are we still subtracting 7? Yeah?
I did
F of negative 6, okay. If you add another 7 to that, you would probably get f of 1. Maybe some of you had that. Another one would probably be f of 8. Maybe some of you had that. Okay, it just depends on how many times you wanted to subtract 7. So f of negative 6 looks like we would get negative 2. All right, if you had 1, notice how you'd have the same value, and if you had 8, you'd have the same value. Just depends on where you would actually fall, but they all have the same height. So far, so good? Okay, what about the next one? Can we find a coterminal x value? Yeah? Negative 4. All right, maybe some of you had 3. Maybe some of you had 10. Depends on how many times you wanted to add 7. But in either case, f of negative 4 is 4. If you had 3, you would still have 4, and if you had 10, you'd still have 4. All right, so it should work out either way. How do we do? Pretty good? All right, so what we're going to do today is make the transition. Yesterday, we were focusing on terminology, like understanding what a periodic function was, how we can determine what the period and the amplitude is of those periodic functions, and now we're going to dive into trig graphs. Okay, so this is going to be on page 411. Our goal by the end of this section is to eventually fill out this front page where we have all 6 trig functions listed, and we're going to be able to identify the domain, the range, the period, and if we have any asymptotes going on for all 6 of these graphs. So we're going to take our time with this. We'll probably only get through maybe 2 or 3 of them today, and then we'll do the rest of them tomorrow. Okay, so our first one is going to be sine. We're not going to write on this page just yet, but we'll come back to it to fill in all of those characteristics. On page 412, though, we're going to explore what the graph of sine looks like. Remember, theta is an angle, right? So we're going to be using our unit circle to help us out with this. If you need to reference it, you can go back and flip in your notes. Hopefully we're kind of familiar with the unit circle a little bit already, so maybe we can fill out these values without having to reference it. Do we know what the sine value is at the very beginning point on our unit circle? If you need to think about the first quadrant to help you out, the first point somewhere over there. What's the sine value from that first coordinate? Can we fill in what that ordered pair would be? Go ahead, Marie. Yeah. It would be 0. Yep, that coordinate is 1, 0. Sine is a y value. So if we plug in 0 for the angle, the sine value would be 0. All right. Let's see. The next angle we're going to check out is pi over 4. That's our 45-degree point, right in the middle of the first quadrant. Can we think about what the coordinate might be, and then therefore what the sine value would be? Yeah?
So we just go to over 2 and then this.
There you go. It's the same for both of them. If you're exactly in the middle, you have the same same ordered pair for both, or same number for both. So the y value, we have the square root of 2 over 2. Now, in terms of graphing, we're eventually going to plot these points to get a picture down below. If you were to type this into your calculator, you'd get a decimal of 0.707. All right, let's try pi over 2. That's 90 degrees at the very top. What's the y coordinate? Yeah. Yes, so this would be 0, 1. The y value is 1. All right, so that's just from the first quadrant. Notice how we're going to work our way all the way around the unit circle, though, because we're ending at 2 pi. So if 3 pi over 4 is the middle of the second quadrant, can we think about what the y value would be from that point? Yeah. There we go. It's the same from the y value in the first quadrant, and we know it's positive because y is positive in the second quadrant. What about the y value at pi? Okay, the very left-handed spot on our unit circle. Yeah? That's the x value. It's okay. 0, good. All right, 5 pi over 4 is in the very middle of the third quadrant. What would that y value be? Good, Rebecca? There we go. It's in the middle, so it's going to have the same ordered pair, but since we're in the third quadrant, we know the y is negative. 3 pi over 2 is at the very bottom of our unit circle. What's our y value there? Yeah? Negative 1, good. All right, 7 pi over 4, very middle of the fourth quadrant. Yeah? We're good. And then 2 pi, if we were to go in a full circle back to where we started, yeah, 0. Awesome. All right, so what we're going to do with this ordered pair table, we're going to plot these points to see what the graph of sine looks like. So let's go ahead and take the time to do that. So we're starting at 0, 0. Okay, we start at the origin. At pi over 4, we're a little bit less than 1. At pi over 2, we are exactly 1. 3 pi over 4, a little bit less than 1. Pi is 0. And we'll repeat the process. So if we were to connect the dots, notice how we would get this wave-looking shape. Could we keep going? Notice how our x-axis goes all the way out to 4 pi.
Excuse the interruption. At this time, all students taking the Keystone Literature test today, all 10th graders should report to their testing sites. Thank you.
Good luck. All right, what would you want to do to keep going? Yeah.
You just like keep adding. It would just be you'd have to go one full circle.
There you go. We're doing one full circle, aka one full cycle, meaning another chunk. Okay, sine is going to be a periodic graph. Because if you want to use the unit circle, we can go around once, we can go around twice, we can go around 3 times, but we're still going to result or end up with the same y values, depending on how many times you want to go around the unit circle. So if we were to repeat the process, at 9 pi over 4, we'd be a little bit less than 1. Pi or 5 pi over 2, we would be 1. A little less than 1. Then 0. And do the same thing underneath the x-axis. So we're just going to develop or draw in another cycle, okay, another wave. You could keep going if you wanted to. Okay, it's going to continue forever. All right, so if this is a periodic function, we should be able to determine the period of a sine graph and also the amplitude. Hi.
Can I make up my test next for you?
Yes.
Okay.
Do you need a pass?
Yes. Thank you so much.
Yep. We need to have like some type of rope for you to just, yep. Mm-hmm.
Yeah, I always consider flipping the word.
I would too. When I first started teaching, I wasn't here, I was at a different school, and my teacher desk was right by the door. So anytime someone would knock on it, I'd have to get up out of my seat, open it, come back down, and then repeat the process. It was so Rachel, I know how you feel. All right, can we identify the period? Can you highlight a certain chunk on this graph, aka a cycle that would repeat itself? Yeah.
The cycle would be one full circle.
One full circle, yep. So you could highlight the very first piece that we drew in. All right, so if the period is one full circle, how many radians does one full circle have? 2 pi. I know, our period is 2 pi. And you can see that on the graph. Notice how we start at the origin and then we're back on the x-axis at 2 pi after we do one full wave. I know, it's all clicking. What about the amplitude? Can we find the baseline, the middle? It's 1. Yep, the baseline's in the middle. It cuts your wave in half. And you go either up 1 unit or down 1 unit. Mm-hmm. What's the radius of a unit circle? 1. Yep. Mind blown. All right, so this is a basic sine graph. It starts at the origin. Maybe we'll write down some of these properties. It starts at the origin. It has a period of 2 pi and an amplitude of 1 unit. Now, at the beginning of the year, we talked about graphical transformations. how we can stretch a graph, shrink a graph, shift a graph, flip a graph. We remember doing all of those, right? We can still apply those transformations to these trig graphs because they're still a graph nonetheless. So let's take a look at those at the bottom. What if I were to take the sine graph and multiply it by 3? Can we dig deep and think about what that multiplication is representing as a change? Yeah.
I don't remember which way, but I know it's a stretch by 3, right?
Yes. Okay, and it's a vertical. Okay, vertical stretch by 3. So we got to take all the y values. Okay, vertical means up and down. If we got to take all the y values and multiply them by 3. So we're going to go ahead and graph this on this paper. Not sure if you want to use a different colored writing utensil or a different type of writing utensil so you know the differences between the graphs. But we're going to go ahead and change this blue graph into the 3 sine of x. So if we start at the origin, what's the y value at the origin? 0. What is 0 times 3? Still 0. So this point, even though we multiplied it by 3, is still going to stay there. That point doesn't really get stretched. Our next easy point is probably this top maximum at pi over 2. That has a y value of 1. If you multiply 1 times 3, it's going to be all the way up there. The next easy point to do is probably pi, because we're on the x-axis, which has a y value of 0. So if you multiply that by 3, that one's not going to move. The next easy one is probably this -1 height, multiplied by 3 would move it down to -3. And then we're back at the x-axis at 2 pi because we did 1 full cycle times 3 is not going to go anywhere. So maybe we'll just graph this 1 cycle. Okay, there's the graph of 3 sine x. Can we identify the period and the amplitude? Yeah? There we go. The period is still 2 pi. We still start at the origin and we end at 2 pi for 1 full wave. The amplitude, however, was changed. The baseline is still at the origin or still at the x-axis, but now notice how we go either up 3 or down 3 to get to that top or lowest point. So what do you think this multiplier of 3 out front is affecting or represents? Can we make a connection? Yeah? That's your amplitude, yep. All right, before we try the next one, let's go back up here. What's the number in front of the basic sine function? 1. And wasn't that our amplitude? Yeah. All right, let's do the next one. Sine of 1/2 theta. This time, instead of multiplying on the outside, which was a vertical stretch, this time we're multiplying on the inside. So can we take a guess about what that might change for this graph? Yeah? It might affect the period. So instead of stretching it up and down, this one's going to stretch it left and right, kind of like an accordion. So this would be a horizontal stretch by what? This is when it gets a little tricky. Let's think about this. If we had x minus 4 squared, do we remember what that minus 4 on the inside did to a graph? It went right 4, okay? So if something's on the inside, it does the opposite of what you would think. We're not horizontally stretching it by a half. Can you think about what we're stretching it by? It's by 2, okay? It's actually the reciprocal. The inside does the opposite of what you would think. All right, so if we're going to stretch it horizontally, meaning left and right, this time we got to multiply the x values. Okay, before we stretch the y values for that vertical one. All right, so we're going to start at the origin. What's the x value at the origin? 0. 0 times 2, still 0, so it's going to stay right where it is. Okay. The next easy point is pi over 2, which is probably that top point. If you double pi over 2, where would we now be located? Pi over 2 times 2? Pi over 2 times 2? Yeah? No, that would be pi over 2 divided by 2. This would just be pi. The 2's would cancel. One's on the bottom, one's up top. Okay? So this point, which was originally a pi over 2, now has to be moved to pi, which was right there. Okay? This horizontal stretch can get a little tricky. We're essentially multiplying by 2 every time, but I'm going to show you a little shortcut to help you do this. Notice how this first point here is 2 units away from the y-axis. So if we double 2 units, we should now be 4 units away. And notice how 1, 2, 3, 4 would make us land right there. So you can think about it that way instead of working with pi's. I know that those can get a little confusing. Let's try the next point. Okay, we're changing the blue graph. So the next point on the blue graph is on the x-axis, which is 1, 2, 3, 4 units away. If we double 4, we now should be at 8. 1, 2. All right, so this point is now moving here. The next easy point on the blue graph is at the very bottom, which is 1, 2, 3, 4, 5, 6 units from the y-axis. So if we double 6, we should have 12 units away, somewhere right there. And the last point in our cycle is at 2 pi. If we double 2 pi, we're at 4 pi, which is at the very end. So if we connect all those black dots, there's our one cycle. Okay, we changed the blue one to the black one. Notice how it's stretched out longer? Okay, so let's try to think about what's the period of this black graph and the amplitude. Yeah? Period's 4 pi. All right, amplitude. Yeah? Still is 1. Okay, so let's take a look at this. The number being multiplied out front is affecting your amplitude. What about the number being multiplied on the inside? What's that affecting? Yeah, your period. Really good, guys. Okay, so we completely finished everything that I wanted to discuss with the sine graph. Let's go ahead and we're going to flip to the front. We're going to fill out some of these characteristics on the chart. All right, so for the sine graph, a little fun fact there. We said it starts at the origin. What's the domain of a sine graph? If you were to continue the wave forever, how far left and right would it be able to go? Yeah? Infinitely. Yep, negative infinity to positive infinity. All right. What about the range? Looking at my blue graph on the previous page, how far low to high does it go? Yeah. Negative 1 to 1. That's your amplitude. Since your baseline was at 0, okay, the x-axis, you either go up 1 or down 1. Remember, this is for the basic one, not any transformed ones that we have. Yeah.
Me and Maddie kind of got lost during that graph. Can you just go back to what you said there?
The black one?
Yeah.
Okay, you want to start from the beginning?
Well, I mean, I'm okay on that, but Maddie, you want to
Okay, we'll go from the beginning. Can I erase the red one? Is that going to be a little confusing? Okay. All right, so the blue graph is the original sine one that we started with. Okay. What we're going to do is we're going to double the period. We're going to stretch it horizontally. So we're going to pick some points on the blue graph and just double their distances left or right. So the first point on the blue graph at the origin basically stays at the origin because it's starting with a value of 0. The next point, the easy point I think would be able to use, is at the very top. And that very top point is 2 units away from the y-axis. So if we double 2, this point should now be 4 units away. So this point is moving here. The next point on the blue graph is probably this x-intercept, which is 4 units away. So this point should be moved to 8 units away, which is at 2 pi, if you count 8 over. The bottom point is 6 units away, so this point should now be 12 units away, somewhere right there. Maybe I'll draw arrows. Okay. And then the x-intercept point, the ending point for the first cycle of the blue graph, is, what was that? 1, 2, 3, 4, 5, 6, 8 units away. So now it should be 16. It's moving all the way over here. So if we connect all those black dots, there's our horizontally stretched graph. Is that okay, Maddie? Okay. All right, so domain, this is for basic sine graph. All real numbers, range -1 to +1. We said the period was 2 pi, okay, 1 full cycle or circle around the unit circle. Did we have any asymptotes in our graph? No, but those might pop up for some other ones. Okay? Let's see. Before we start cosine, we'll probably do that one tomorrow, but I have one more question for you. What if I were to give you 3 sine of theta plus 2? Can we think about what that graph might look like? Or how this blue graph would be changed? Yeah. Okay, so our previous red graph looked like this, right? Because that was the 3 sine. We just got to move everything up 2. If you move everything up 2, the baseline moves as well. Because isn't the baseline considered the middle of your graph? So if you move the graph, you're moving the middle. So if we were to move this up 2, anything being added or subtracted on the end is where your baseline is. Okay, where the middle is located. We're not going to dive too deep into that, but that is a characteristic worth noting, I would say. Does that make sense, though? We talked about those shifts going up or down. All right, we'll save cosine for tomorrow. Going to look very similar. These are going to start to get a little bit quicker now that we know what we're trying to look out for, but we still have 5 more graphs to do.